Set theory is a fundamental branch of mathematics that deals with the concept of sets, which are simply collections of objects. These objects can be anything: numbers, letters, or even other sets. Imagine a set as a box containing different items. For example, consider the set of fruits: apple, banana, orange. Each fruit is an element of that set. Now let's dive into some essential operations we can perform with sets. The first operation is the union of sets. If we have two sets, say equals 1, 2, 3, and b equals 3, 4, 5, the union, denoted as a union b, combines all the elements from both sets, giving us 1, 2, 3, 4, 5. Notice how the number 3 appears in both sets, but is listed only once in the union. This brings us to an important principle: sets do not allow duplicate elements. Next up is the intersection of sets. This operation finds the common elements between two sets. Using our previous example, the intersection of A and B, written as A intersection B, results in 3, since that's the only number present in both sets. This concept is particularly useful in various fields, such as statistics and probability, where we often need to analyze shared characteristics. Then we have the difference of sets, which tells us what's in one set, but not in the other. For instance, B would give us 1, 2, since those elements are in A but not in B. Conversely, B, it would yield 4, 5. This operation helps us understand relationships between different groups. Moving on to the algebra of sets, we encounter several important laws that govern how these operations work. One of the most significant is the commutative law, which states that the order of union and intersection doesn't matter. So, a union B is the same as B union A, and A intersection B equals B intersection A. This property simplifies many calculations and proofs in set theory. Another key aspect is the distributive law. It tells us how intersection and union work together. For example, intersection B union C is the same as intersection B union A intersection C. This means we can distribute the intersection over the union, which is a powerful tool when dealing with complex set expressions. Now, let's touch on the concept of duality in set theory. This principle states that every statement or theorem about sets has a dual statement that can be derived by swapping union with intersection and vice versa, while also replacing the universal set with the empty set. For example, De Morgan's laws illustrate this beautifully. The complement of the union of two sets is equal to the intersection of their complements. This duality not only deepens our understanding of set operations, but also highlights the symmetry inherent in set theory. To wrap up, set theory provides a robust framework for understanding collections of objects and their relationships. From basic operations like union, intersection, and difference to the algebra of sets and the elegant concept of duality, these principles are foundational in mathematics and beyond. Whether you're analyzing data, solving problems, or simply exploring the beauty of mathematics, set theory is an essential tool that opens up a world of possibilities.